sir.
Okay. Recording start हुआ या नहीं हुआ? हाँ, recording started. Okay, fine. Okay, so let's start with this. Okay, I'll give you some introduction towards Gaussian first. थोड़ा बहुत. Okay.
Okay.
So that is Gaussian functions. Okay, so what do we have usually as a Gaussian? We represent p of x as 1 by 2 pi sigma square root of 2 pi sigma
Under
e power minus x minus mu whole squared by sigma squared, and there is a half outside.
yes.
Okay, so mu is our mean here and sigma is our variance.
Yes.
Okay, now we all know this very nice diagram where this is mu and sigma will be similarly something like this. Fine. Just a representation. This need not be anything that we want. Now, what if I change this mu? It will only get shifted.
Shift.
Yeah. If we change this mu, it only gets shifted. Shifted somewhere like this for some different mu. Fine. Now, what happens in n dimension? What is the Gaussian in n-dimensional space? Okay, before discussing that, let us see this. Suppose I have just this R2 plane. Okay. Now, let me take some area. Say this area.
Okay.
Say its area is some A. ठीक है. A is the area of this enclosed figure.
Okay.
Now, what I do is, if I rotate this axis this way, will it change the area?
No.
No, right? See, if I initially want to represent this area, let me take a line integral along this, or some integral. Let's say I am integrating some, or not the area. Suppose I am integrating some function, say p of x, on this.
Okay.
So it might actually be p of x comma y, or it depends on both x and y. On each point, here I am asking you to see that there is some surface over this. Okay, there is a what do you call? There is an outward projecting z. Okay, towards us. So what happens is I am assuming a curved surface or a surface over it. Okay, and say and that surface is p of x comma y. Okay, this is x, this is y. Okay, so if I integrate p of x comma y over this area, say this area is A. I have already represented A here. Okay, so I am integrating over this area, and I have dx dy. Say it is some r. Okay. So A, here A is the enclosed region. Okay, region enclosed by this. Region enclosed by this. Okay, this is clear.
Yes.
Now say I have shifted this to some x dash and y dash. Right.
Okay.
Now I'll have a new function p tilde, है ना? Some p tilde in x dash and y dash. I just make the transformation from x to y. Whatever the transformation is.
Yes.
Okay, and then I have dx dash and dy dash, and the area is now again the same. It's the same area. Now what will this integral evaluate to? Same r, no?
Same होना चाहिए.
Same होना चाहिए, because area is invariant whatever my coordinates are. Similarly, if I take some other x dash y dash, x double dash y double dash somewhere over here, Will it change the area? No, it won't, right?
It won't.
So that will be like integral p, say 2 tildes of x double dash y double dash dy double dash dx double dash is the same r over the same area.
Yes.
है ना?
हाँ.
Fine. Now, say there are something called rotation matrices.
Yes.
Okay. So what are these rotation matrices? Let us derive the rotation matrix. Okay, let us derive it so that you have a clear feel towards it. Say this is your x, this is your y. Okay. Now, let us say this is our complex plane. Okay. So this will be real part of z. This will be imaginary part of z. This is how it is. Now,
Yes.
now if I take some x plus jy here, and let us take just some unit 1 of unit 1 at angle theta from this. Okay. So, and then let me say I want to rotate this at an angle phi.
Okay.
At 1. Okay. Now, what will these coordinates be? It will be cos theta, comma sin theta,
Sin theta.
and this will be cos theta plus phi, comma sin
Cos
theta plus phi.
Yeah.
है ना? Isn't it? This is how they are. Now, what I want to do is I want to write this as cos theta plus j sin theta, and this as cos theta plus phi plus j sin theta plus phi. Okay.
Yes.
If this is say r1, this is say r2, you can see that this is e to the power j theta, and this is e to the power j theta plus phi. So this is simply r1 times e to the power j phi. Okay. So this is how we prove simple rotation, not a matrix, simple rotation using e to the power j phi. Similarly you can scale, but we just want rotation here. So we can generalize this as you have any x plus jy. Now you rotate it with theta. What will happen? This will be e to the power j theta times x plus jy.
Yes.
Right. Now let this be the new x dash plus jy dash.
Okay.
Okay. Fine. So what you have? X plus jy times e to the power j theta, which is x plus jy times cos theta plus j sin theta. That will be x cos theta minus y sin theta plus j times x sin theta plus y cos theta. Okay, this will give you your new x dash plus jy dash.
Oh, nice.
Okay, so x dash will be x cos theta minus y sin theta, and y dash will be x sin theta plus y cos theta. है ना? Now if I take this to the next board, so you have this. Now we write this in matrix notation. Cos theta minus sin theta and sin theta cos theta, isn't it? Times xy.
And xy.
Okay. Now
Okay.
Now I want to see here. Now I want you to see here in the Gilbert-Strang way. What is that? Tell me what is that? It is cos theta sin theta x plus minus sin theta cos theta into y. Okay, so this is your x dash y dash. What does this mean to us physically? Physically it means that I'll tell you. We have this original xy. Now let us try to plot this vector cos theta sin theta. How will that look like? It will look like some theta angle, and वो होगा, it will be this way. This. Okay, theta. So this is your cos theta sin theta. Okay. Now the other is minus sin theta cos theta. So that will be if you write minus sin theta cos theta, if you want to represent this as something, you could write this as cos of pi by 2 plus theta, and this as sin of pi by 2 plus theta, right? So just have pi by 2 from here. Then this will be your minus sin theta and cos theta, right? Okay. You already see here that these are perpendicular from the dot product of these two. Okay, if you define a bar as cos theta sin theta and b bar as minus sin theta cos theta, then a bar transpose b bar will be 0. You can see that from our simple dot product cooperation. Then that is how it is. So now that is why there is this angle pi by 2, and that is not of a surprise now. Fine. Now what are we saying in this? When we are saying that you are doing a rotation, so this is a rotation matrix. We derived this saying this is a rotation matrix. Rotation matrix. Now what are now let us plot this for some xy which was this way. This was some xy. Say let us write x0 y0.
Okay.
Now if you rotated this with an angle theta, this x0 y0 what was with respect okay, not this, just see this. How have you obtained these things, cos theta and these things? By rotating x axis by theta and y axis by theta.
Yes, sir.
Do you see that? So now let us try to see this as the new coordinate system. Okay, in the new coordinate system, see cos theta sin theta times x plus minus sin theta cos theta times y. What is this? This is your basis vector. This is like one of your basis vector. This is like other basis vector. So what I want to tell you here is, if you have a rotation matrix, say this was your rotation matrix, the columns of the rotation matrix will give you basis vectors of the new frame. Okay, if you are rotating a complete frame, okay, a complete coordinate system, do you get that? You are rotating a complete coordinate system, then in that case this rotation matrix will give you what are the new bases, the columns of this rotation matrix. So let us write that. Columns of the rotation matrix will give us the new orthonormal basis. That is the new basis in the rotated frame. Okay, do you get that now?
Yes.
Good. Now how do I want, now I want to reflect this idea in this areas concept. Okay. Okay, so let us consider let us come back to Gaussians and go somewhere behind.
Okay.
Let us come back to Gaussians and go somewhere. Okay, so let me say your p of x is 1 by 2 pi square root of 2 pi e to the power minus x. Let us for the present consider this as 0 mean. Okay, we can shift appropriately whenever necessary. So this is x square by 2 sigma 1 squared. Let me call this x1. Okay, now let me have another variable independent of x1, which is x2, and I write it 2 sigma 2 squared. Okay, so this is our first Gaussian. In the sense it corresponds to the first random variable x1. Okay, this corresponds to the random variable x2. So this will be sigma 2. So we go on up to say xn 2 pi. There is a sigma 1. Okay, sigma n e to the power minus xn squared by 2 sigma n squared. Fine. Now here we consider x1, x2, so on up to xn are independent. They are not IID, they are only independent. Okay, because IID must mean that all of these are same. Same. Okay. So as to avoid ambiguity, we have to write it this way. Okay. Now say we want to know the joint distribution of this. Joint distribution of x1, x2, so on up to xn. Why are we talking about joint distributions? Why are we talking about? Tell me, try to tell me.
Conditional density.
No. That is a different point of view. That comes after talking about joint distributions. But here we are talking about joint distributions because we want to have these kind of things. Do you see this? See, it is like I want to have a combination of this. So I have to talk about a distribution that involves all of these. Okay, even if one thing changes, that's a new distribution. That's a new combination again. If I have a set of these like 1, 2, so on up to n, say this is one vector R1. Even if this changes to R2, if this 2 changes to 1, it's a new vector altogether. So each change will reflect a lot of things. So when we want to discuss about something like this, we want to keep track of every change in x1 to xn. So we want to talk about joint distributions. Okay. So since these are all independent, we assume independence condition. So independence of xi's imply the joint distribution as p of x1, x2, so on up to xn is x1, x2, so on up to xn. This is how we write joint distributions. This is 1 by square root of 2 pi power n. We multiply all of them. This will be sigma 1, sigma 2, so on up to sigma n. Okay. Then it will be e power minus x1 square by 2 sigma 1 square plus x2 square by 2 sigma 2 squared plus so on up to xn squared by 2 sigma n squared.
Okay.
Okay, so this we'll write as 1 by square root of 2 pi power n sigma 1 to sigma n e power minus half times x1 square by sigma 1 squared plus so on up to xn squared by sigma n squared. Okay, this is clear. Now
Yes,
let
yes,
us, for example, only take a two-dimensional case for visualization. This is your x, this is your y. Okay, and here lies your p of, okay, this is your x and this is your x1 and x2. This is p of x1 comma x2. Okay, so if we try to plot this, how does that look? 1 by 2 pi, it is just 2 pi times sigma 1 sigma 2 e to the power minus a half times x1 square by sigma 1 squared plus x2 squared by sigma 2 squared, right?
Yes.
Now how do the contours of this, we know that this is this Gaussian, isn't it? This Gaussian looks something like this, a circular kind of thing, elliptical kind of thing.
Elliptical.
So we know this. This is in the air. तुम्हें वीडियो दिख रहा है? हाँ, ओके,
हाँ दिख रहा है.
हाँ दिख रहा है ना?
दिख रहा है.
Okay, so now if I want to draw its contours, how do I draw it? It will be, okay, wait,
Ellipse होगा.
हाँ, elliptical होगा, and okay, let us draw the contours here.
हाँ, okay.
There will be something like this.
Yes.
है ना? है कि नहीं? हाँ. And if you want to represent this as a colored contour, a colored contour in a manner that, wait, yeah, light colors give you a feel of lower height. Okay, if the color is light, the height is lower.
Okay. अच्छा.
Okay.
Okay.
हाँ.
From the.
Yeah. If the color is high, if the color is darker, then the height is larger.
Larger.
Okay. Fine. Now, this is how the probability density is. Now, if I am doing an experiment and if I am picking things from this, if I am picking what you call data.
Okay.
So this is your x1, say this is your x2. Similarly, this is your x1, this is your x2. If I am doing a random experiment where the data coming, say this is your box, there is a box here, okay, and it is generating data.
अच्छा.
Okay, and it is generating data, these points, data is these points, x1, x2. Okay, and these are distributed according to this. These points are distributed according to this. Fine.
Okay.
These points are distributed according to this distribution. So, how do I get this? Is my question. I get something like this. I'll show you. In this region, they are very dense. As you go away, the density reduces because of the lighter colors.
Lighter colors.
है ना? Because the colors are light, what happens? You do not have
Enough.
the probability of getting there is very low.
Low.
The probability here is very high. Okay, as you are moving away, the probability is decreasing. As you are moving away, the probability is decreasing. Now these could be very elliptical. I have drawn not that elliptical. These could also be very elliptical depending on sigma 1 and sigma 2. है ना?
Yes.
Depending on sigma 1 and sigma 2, these can be elliptical to a very large extent. What I mean is, these contours could be this way. Do you see that? These contours could be as bad as this. And then that is what happens. Fine. This is okay. Now if sigma, so say this here, it corresponds to sigma 1, and here it corresponds to sigma 2. What can you tell me about sigma 1 and sigma 2? Sigma 1 is larger than sigma 2. See, since sigma 1 is larger, see, what are you indeed doing? What are you indeed doing is you are making this a constant to draw that. है ना? So that's an ellipse. Yeah. So what are we doing is, we are doing x1 squared by sigma 1 squared plus x2 squared by sigma 2 squared is equal to constant. And we are changing this constant to draw different ellipses. Say this corresponded to C1, C2, C3, C4. If sigma 1 was larger, this is larger. है ना? If sigma 2 is larger, sigma 2 is smaller than sigma 1. So this corresponded to sigma 1 and this corresponded to sigma 2. So sigma 1 is larger than sigma 2. We call this major axis, no? Major or minor axis? Major axis and minor axis.
Major axis, minor axis.
है ना? This minor axis of an ellipse. Okay? Fine until this point. Now, now what I want to do is, now let us say I am rotating this. I am rotating this. I say I want to rotate every point in this plane by some theta. Okay, every point in this plane by some theta. So how will the resultant look like? The resultant ellipses will look like this.
Right.
This is rotating each sample by theta. So that a change is reflected in x1 and x2. Isn't it?
Yes.
Now so what will the new x1 dash be? New x1 dash and new x2 dash will be cos theta minus sin theta cos theta times x1 x2. Isn't it?
Yes.
Now let us observe this. Let us see what change will the new px1 x2 px, है ना? We add this px1 x2. x1 x2 in terms of x1 and x2. That this is 1 by 2 pi sigma 1 sigma 2 times e power minus x1 squared by sigma 1 squared plus x2 squared by sigma 2 squared. Okay, we want to make some change here so that something of this, so that this gets used.
So that we can use this matrix to get the new density.
So I'll write this as minus half times.
Like quadratic form.
The quadratic form. Okay, I write it this way. Now what do we have next is 1 by 2 pi e to the power minus x, what is that, a half, and then you have I'm writing it again. I am telling this to you so nicely because I want to use this in teaching some other stuff also. I want to teach you Kalman filtering if possible. That time this will be very useful. Even now it is very useful in understanding what I want to teach next. Okay, so yeah, this is what I get. Fine.
Okay.
Now what the substitution I want to do is this. I want to make this substitution. So let us copy this. Since I want to do this substitution, I need to have something like this. x1 x2 is cos theta minus sin theta cos theta inverse, isn't it? The inverse of this matrix, whatever it is. I want to have the inverse of this matrix. Now that inverse will simply be replacing this theta by minus theta, because we know that they are rotation matrices, है ना? We know they are rotation matrices, so you just replace theta by minus theta. That will become so you need not explicitly calculate rotations. Inverses of rotation matrices. I will give you something very similar to what we did here. This is all from matrix theory only. I will give you something very similar to what we did here, but when we go into n-dimensional space. Okay, this is clear.
Okay.
Now, so let us, there is a sigma 1, sigma 2. Okay, now let us replace x1 and x2 with this. So similarly, you have x1, x2 as cos theta minus sin theta cos theta do you see this? Transposing on both sides. है ना? A, what is, if A is equal to BC, A transpose is C transpose B transpose.
C transpose B transpose.
That's what I did.
समझ गया.
You understood, no?
Yeah.
Now we want to plug, so let us make this all small.
तेरा lunch हो गया क्या?
No, I'll go at 1:45.
अभी टाइम कितना हुआ?
1:15 या 1:17 1:20 कुछ हुआ है.
Okay.
See, I want to complete something. Once I complete that, I'll go. And we'll continue after.
वापस पढ़ रहेगा ना?
We'll continue after that.
आज तो तेरा छुट्टी है.
हाँ, मेरा छुट्टी है. ओके, फाइन. मुझे एक कूलर ख़रीदने जाना है. आई विल गो एट 5. क्योंकि साला यहाँ 45 डिग्री सेल्सियस तक जाता है रे. सॉरी 50 डिग्री सेल्सियस तक जाता है दिमाग. हाँ, सो विल सब्स्टिट्यूट दिस हियर.
मतलब वो इनिशियल फॉर्म.
हाँ, ओके. सो व्हाट विल दैट बी? 1 by 2 pi sigma 1 sigma 2 e to the power minus half x1 dash x2 dash times cos theta minus sin theta cos theta. This will be 1 by sigma 1 squared 1 by sigma 2 squared 0 0, and then this is cos theta sin theta minus sin theta cos theta x1 dash x2 dash. Okay, this is fine. Now let me tell you something called properties of rotation matrices. For any setting, say R is a rotation matrix. Okay, so what it does is, if V and U are two vectors in Rn, where the angle between them is defined by their dot product, which is V transpose U. So V transpose U, say V and U are two unit vectors, okay, so as to reduce our notation, norm notation. This will be some cos theta, okay, in n dimensional space, where the theta is an angle in n dimensional space, है ना? Now see, when two vectors are rotated, the angle between them is the same.
Obviously.
Even in any space, it should be in any space. In any space, the angle between them should be the same, है ना?
Yes.
So we have the angle between RV and RU. Angle between is the same as angle between V and U. So you want V transpose U is the same as RV transpose RU, which is V transpose R transpose RU. Okay.
Yes.
Now a very nice thing to do here is make R transpose R is equal to I. This will become V transpose U. Do you see that? So the angle is preserved. If I call R is a rotation matrix, if R is chosen in this way, okay, then angle is preserved. Okay, fine.
Yes, yes.
Now, if R transpose R is I, that implies R transpose is R inverse.
Yes.
Okay. Now I said I'll tell you something. No, that is this something. Now say in R2 you have rotation matrix for theta as R theta is cos theta minus sin theta cos theta, and R of minus theta, which is the inverse. R theta inverse is cos theta minus sin theta cos theta. Do you see that this is the transpose of the first one?
Yes, yes.
That was what I wanted to point it out here.
Sure.
Okay, here. Fine.
Nice.
So, okay. Now, if you went into an n-dimensional space in the same situation, in this situation, if you went into an n-dimensional space, so what was this here? These two were your r theta, and this was your r minus theta.
Minus theta.
Or you can also write it as, or this, if you said this was r minus theta, this is r theta. है ना? हाँ, so if one is r theta, the other is r theta transpose.
Yes.
If one is the rotation matrix, the other is the rotation matrix transpose, because transpose and the inverse are the same.
Same.
Here, because we transposed this, I am writing it as transpose here. Do you see that?
Okay.
We transposed this. We've got this by transpose form. This is just the transpose form of the above expression. Since I did a transpose here, I am writing a transpose here. Or else I could also have written an inverse. Okay. Yeah. Now, if we went into an n-dimensional situation where we cannot visualize the contours, this will be 1 by root 2 pi power n, and there will be sigma 1, sigma 2, so on up to sigma n. Fine. And after that, you will have e to the power minus half times x1 dash, x2 dash, so on up to xn dash times a rotation matrix transpose, right, where R is a rotation matrix in
N-dimension.
R is a rotation matrix in Rn. Okay, so this will be R transpose, and then I have this 1 by sigma 1 squared, 1 by sigma 2 squared, and so on up to 1 by sigma n squared. And then there will be this R, and after that there will be what?
X1 is 2 dash the column vector. Okay.
That will be x1 dash, x2 dash, xn dash. Okay. Now, what did I do?
Change of basis.
Okay. By change of basis, what did I do? See, wait. Let us discuss something before coming to this.
तो आया क्या?
No. Let us discuss something बोला. अच्छा, sound आया क्या आप पे हो? हाँ, that was message आया. Okay. Now, suppose I have some x1 and x2. Okay. If I am collecting data. Suppose the data that I got is in this way. Now I am using an example from BP Lathi, if you can remember.
BP Lathi में तो बहुत सारे examples हैं.
No, this is the unique thing in BP Lathi. Now, what do I define for this data? What do I see for this data? I see that the data mostly lies in this region x1 greater than 0 and x2 greater than 0, as well as x1 lesser than 0 and x2 lesser than 0.
Yes.
And in this region where x1 is greater than 0 and x2 is less than 0, and when x1 is less than 0 and x2 is greater than 0, this data doesn't lie very much. So I say the product x1 x2 is greater than 0 is mostly present in this data for most points. In this data. Okay, all this data is zero mean data. Okay. Because for any data we can convert it into zero mean data by subtracting it with its mean.
It's mean, yeah.
Okay, so for most points in this data x1 x2 is greater than 0. So we define something called sigma x1 x2 for each point I from I is equal to 1 to the number of points, say capital N. This as the covariance of x1 comma x2. Isn't that?
Yes. With obviously 0 mean.
है ना? Now what if I collected data with this x1 dash and x2 dash?
Achha.
I would, then what would happen? Then something like this would happen. It would look something like this, isn't it?
With respect to x1 dash and x2 dash.
This is x1 dash and x2 dash. When it is looking like this, I have almost the same number of points in each of the quadrant. So in this case, the definition of covariance of x1 dash and x2 dash will be 0. Why? Because this is giving some positive 5 contribution. This will give you some negative 5. This will give you some positive 5 again. This will give me some negative 5 and this will give me 1. Do you see that? In this, there are mostly in this and there are very less in this. So this will give a very less negative contribution. In this, it is equally distributed in all. So this will give me, if this gives me some positive 5, this will give me some negative 5. This is giving me positive 5, this will give me negative. Okay. So here the covariance is 0.
ये अच्छा है.
हाँ, ये सब कुछ अच्छा ही है. देखो. Now everything will correlate. Okay. Fine. Okay. Now, once this is done, do you see what we are doing by rotating? I am trying to see. These have become 0 now. These are the covariances. Okay, from 0, see, I have a Gaussian where the covariances were actually 0. I have rotated that so that I get to a Gaussian that we are finding in nature, where the covariances are not 0. Do you see that? Say hypothetically I am able to do this. I may not be able to do this because I don't get data in this form. Suppose that I am able to get data in a form that there are only variances and there are no covariances.
No covariance.
Okay, suppose that I was able to fix a basis there. And suppose this was God. Okay, God was doing this.
So wait. So hypothetically you are supposing that?
No, not me. God. Okay, God is supposing that all data, He has all data only in terms of its so that they don't relate, they don't depend on each other.
In form of coordinates of x1 dash.
X1 dash and x2 dash where they don't depend on each other. Okay, see, this is because they depend on each other. Because x1 and x2 are depending on each other, this is happening. If they did not depend on each other, this would happen. Suppose God had this, God made some alterations to it and sent us this data. Okay, and that alteration is captured by this R transpose and R. Because R transpose and R, the columns of R transpose and R are what? Columns of R are
the basis for
the basis of the rotated frame. है ना? Fine.
Okay.
Now this R transpose 1 by sigma 1 squared, 1 by sigma 2 squared, so on up to 1 by sigma n squared R is equal to Cx, called the covariance matrix. Okay. So called the inverse of the covariance matrix, because you see these are inverse variances. These are inverses, no? So we have this. We call this the inverse of the covariance, because it is containing these. And R transposes are inverse of each other. Okay. So we have this Cx as R transpose or R inverse. Anything is okay. 1 by sigma 1 squared, 1 by sigma 2 squared, so on up to 1 by sigma n squared. 0 0 times R.
Cx.
Cx inverse.
Acha, okay.
Okay.
The entire thing.
The entire thing. So Cx will be what? This will be R, because this will be R transpose again. Sigma 1 squared, sigma 2 squared, sigma n squared, R. Inverting,
Inverting.
See, this is your covariance matrix.
Oh, the entire thing.
Now, this is a diagonal matrix. This is a matrix which is the inverse of this.
Yes.
So what is this called? Say AV is equal to VD. Then I write A is equal to VD V inverse. What is this called? Eigenvalue decomposition.
Eigenvalue decomposition. Oh, Rm. Oh. Eigenvalue decomposition.
Okay. So this is the eigenvalue decomposition